8A, Introduction to Hypothesis Testing. So in section 7 we were dealing with confidence intervals, which basically we were estimating what happened in the population based on what happened in a sample. And now with hypothesis testing, what we're going to do is we're going to actually be testing people's claims and saying if they make a claim about the population, let's use a sample to test that and see if that claim is reasonable or not. Right? And when dealing with this, I like to bring up a claim of my own that any number squared yields a positive result. So any number squared yields a positive result. So that's my general statement. And this is where I would normally ask a class to prove that, because I ask people, is that true statement? And those people who believe it's true raise their hand, and pretty much the whole class raises their hand, because we know if you square a number, you get a positive result. So I say, prove it. So people start telling me, well, if I take -5 and I square it, I get 25, which is great. That shows that -5 squared is positive 25. But does it show that all numbers squared give you a positive result? No. So people go, well, oh yeah, and 3 squared is equal to positive 9. Again, showing that this positive number, when it's squared, gives a positive result. And we start looking at it and going, well, that's great. That proves that this number squared gives a positive result. It proves that this number squared gives a positive result. But does it prove that all numbers squared will give you a positive result? And so the determination usually comes up that how can we do that? How can we prove that any number squared will give a positive result? And that's by testing every single number. And then I usually assign someone in the class to go and do that for us, and they refuse adamantly because they know there's an infinite number of numbers, so they would never be able to finish that to prove that it works for every single one. And that's where I come in and I say, but 0 squared is equal to 0. 0 is not positive. Therefore, I just proved this statement false, because our statement was that any number squared yields a positive result, and the reality of it is no. 0 squared does not yield a positive result. So what we want to say is any real number squared yields a non-negative result. But what's the point of this? Well, the point of this is that it's not easy to prove a general statement to be true. If I say that everybody likes pizza, it doesn't matter how big my sample is, and everybody in the sample says that they like pizza, that doesn't prove that everybody likes pizza, but it's very easy to prove a general statement false, because all I need to do is find one time where it's not true. And that's what I did here. So it's very easy to prove something false, a general statement false, because you only need one time that it's not true. It's very hard to prove a general statement true, because you have to prove it true, you have to prove that it's true every single time. And this is going to be part of what we deal with hypothesis testing. Now, when we're talking about hypotheses, you're familiar with a hypothesis. And if I ask you what's a hypothesis, the first thing that comes to your mind, because of all your science classes, is an educated guess, right? A hypothesis is an educated guess. It's not a proven fact, it's an educated guess, meaning we have some information that allows us to make a judgment call on it. And usually it's a reasonable judgment call. But it doesn't mean that it's necessarily true. You then test your hypotheses and verify are they correct or not. Now, when we're dealing with hypotheses for our hypothesis testing, there are two types of hypotheses that we're going to deal with. One is H sub 0, or H sub O, known as the null hypothesis. The other one is H sub A, known as the alternative hypothesis. So the null hypothesis, H sub O, and the alternative hypothesis, H sub A. So we use both of these together when we deal with hypothesis testing. Now what I'm going to do is I'm going to get rid of the names, so that's null hypothesis, alternative hypothesis. And I'm going to show you what they relate to. When we're dealing with a null hypothesis, we're dealing with equality. So less than or equal to, greater than or equal to is a null hypothesis. It always includes equality in it. Less than or equal to. That would be like at most. You can have at most 5 people in an elevator at a time. At most means I could have less than 5 people. I could have 5 people, but I can't have more than. At most. Equal. You can have 5 people in an elevator at a time. 5. You have to have 5. You need to have at least 5 people in an elevator. At least, so you can be more than 5, or it can be equal to 5, but you can't have less than 5. So our null hypothesis always deals with less than or equal to, or greater than or equal to. Whereas the alternative hypothesis is the complement of the null hypothesis. Remember that the complement meant everything else, the rest. So if the null hypothesis is less than or equal to, everything less than or equal to, then the alternative hypothesis must be greater than. That's everything else. This is equal to, and anything to the left of anything less than it. Then the alternative hypothesis, the complement, is everything else, whatever's to the right of it, what's greater than it. If the null hypothesis is equal to, then the alternative hypothesis is not equal to. And if the null hypothesis is greater than or equal to, then the alternative hypothesis will be less than. So they're always the complement. And notice that the arrows go the opposite directions. If it's pointing to the right for the null hypothesis, it's pointing to the left for the alternative hypothesis. If it's pointing to the left for the null hypothesis, it's pointing to the right for the alternative hypothesis. If it's equal, then not equal. Equal to 5, not equal to 5. Right? Now the nice thing about this is that both of these have very specific things that they do. We always test the null hypothesis. So the null hypothesis is always what we're testing. And we always use the alternative hypothesis to test it. So there are 3 types of tests that we deal with. We deal with a right-tailed test, a two-tailed test, or a left-tailed test. And I'll explain a little bit about those in just a little bit, but the alternative hypothesis always points the direction to what type of test we're dealing with. So the alternative hypothesis always tells us. And I say it points the way because if it's greater than, if the alternative hypothesis is greater than, then that's pointing to the right and it's a right-tailed test. If it's pointing to the left, if it's less than, pointing to the left, then it's a left-tailed test. And if it's not equal to, there's this slash that's cutting it into 2 pieces, so it's a two-tailed test. So we always test the null hypothesis. We use the alternative hypothesis to determine what type of test we're going to do on it, whether it's right-tailed, two-tailed, or left-tailed, and the alternative hypothesis always points the way to that. So let's quickly take a look here and say, well, if I know that the null hypothesis is that mu is greater than or equal to 7, it includes equality, so it's the null hypothesis, then the alternative hypothesis is going to be mu less than 7. And that tells us we're going to use a left-tailed test. Now, remember I said with hypothesis testing that we're actually going to be testing the claim that people make. People make claims about populations. They say the average amount of such and such is. The average weight of an adult male is 196 pounds, or whatever the case may be. That's a claim that they're making about the population. We're going to test that claim. Now that claim can be either the null hypothesis or the alternative hypothesis. So it can be either one. We have to look at the claim and see which it is. If I make a claim that the average grade on the final exam is over 77, over is greater than, the claim is the alternative hypothesis. If I make a claim that the average age of students in my class is at most 23, less than or equal to, a null hypothesis. So we always have to determine whether the claim is the null hypothesis or the alternative hypothesis. And we do that by looking at what is it? Does it include the equality or not include equality? Now, when we're doing hypothesis testing, there are two types of errors that can occur. And I'm not talking about mistakes people make, but I'm saying there are two types of statistical errors that we account for. And mathematicians, being very clever as we are, name them as a type 1 error and a type 2 error. Like I said, very clever in our naming of these. Now, a type 1 error is when we reject a null hypothesis when it's actually true. So, H sub O rejected. Remember, we're always testing the null hypothesis. So in a type, oh, I wrote that in the wrong spot. A type 1 error is when the null hypothesis is rejected when it is true. So basically, we rejected something when we shouldn't have. That's a type 1 error. The probability of making a type 1 error is equal to alpha. And we call alpha the significance level. So alpha, that's the Greek letter alpha, looks like a fish, okay? Greek letter alpha is the significance level, and that is the probability that we make a type 1 error. A type 2 error is when we didn't reject the null hypothesis when it is false. So the null hypothesis was not rejected. When it is false. So basically, when we should have rejected it, we didn't. And the probability of making a type 2 error is beta, that's the Greek letter beta. And I'm not going to give you any name for it because we're not going to deal with that. Okay? We're going to deal with alpha. That's what's going to matter to us, the significance level. But the probability that we didn't reject it when we should have is beta. So our type 1 error and type 2 error, we work with type 1 errors. So let's take a look at this a little bit and see where we're going with it. Well, first of all, remember we're testing these claims. The claims are about population parameters. So we may deal with claims about the population mean. We may deal with claims about the population proportion. Or we may even deal with claims about the population standard deviation or the population variance. Now in this course, we're not going to deal with hypothesis testing for these two, but I am going to state what we're doing with this. So these are the population parameters. The population parameters. And to test a claim, we need a test statistic. Okay? So the test statistic that we'll use is the equivalent sample statistic of these population parameters. So I'm going to call this test statistic. Test statistic. So if we're trying to test a claim about a population mean, then we're going to use a sample mean to test it. If we're trying to test a claim about a population proportion, we're going to use a sample proportion to test it. If we're testing a claim about a population standard deviation, we'll use the sample standard deviation to test that. And if we're testing a claim about the population variance, we would use the sample variance to test that. So if the claim is one of these, about one of these parameters, we would use these associated test statistics to test that claim. And I'll go even a little further to say what distribution we would use under what circumstances. So if we're testing a claim about a population mean, just like we did with confidence intervals when we were finding confidence intervals for population means, we will use the z-distribution, and I'm just going to put distribution here, but we would use a z-distribution if n is greater than or equal to 30, or our population standard deviation is known, and we would use the t-distribution if n is less than 30 and the population standard deviation is unknown. Now you should recognize that as being the exact same method that we used for confidence intervals to determine whether to use a z-distribution or a t-distribution. If we have a large sample or we know the population standard deviation, then we can use the z-distribution. If we don't have a large sample and we don't know the population standard deviation, remember the only way you have the population standard deviation is if it says specifically the population standard deviation is. So if we don't have a large sample and we don't know the population standard deviation, then we use the t-distribution. If we're testing a claim about a population proportion, then we always use the z-distribution. And if we're testing a claim about the population standard deviation or the population variance, then we use the chi-square distribution. And that's that fourth page of the tables that we haven't used and we will not use in this course. But just to see, that's the distribution that we'd go to if we were dealing with a claim about a population standard deviation or a population variance. But we're just going to deal with claims about a population mean or claims about a population proportion. Okay. So we still have a few more things to discuss to get us ready where we can start utilizing this. So we talked about the tails, a right-tailed test, a left-tailed test, or a two-tailed test. I just want to show a little bit with that. What we mean by that is when we were dealing with confidence intervals, remember that I showed this thing where we had the confidence interval, I said the percentage or the confidence level was that area in the middle, and then you had the two tails divided evenly. Well, when we're dealing with hypothesis testing, we can have either a left-tailed test, where you have this area here, and then alpha, our significance level, is in that tail. So that's a left-tailed test. And remember, we have a left-tailed test when the alternative hypothesis is that mu is less than some value, whatever it happens to be. I'm not putting a number in there, but we have a left-tailed test when we have an alternative hypothesis that is less than. A right-tailed test, which occurs when the alternative hypothesis is that mu is greater than some value. Remember, the alternative hypothesis points the way. Alternative hypothesis less than, it's left-tailed. Alternative hypothesis greater than, it's right-tailed. It's pointing the direction. And then we have a two-tailed test when the alternative hypothesis is that mu is not equal to some value, and that splits it into two tails. Now, I said alpha was in that tail there, alpha is in that tail there, but then in the two-tailed test, just like with confidence intervals, we said that the area in the tails are split evenly between them. So for a two-tailed test, we have alpha over 2. So basically half of alpha in each of those tails. So this is getting us closer to what we're going to need. Now, what we are going to use initially for testing hypotheses for a population mean is we're going to use p-values. So let me clear this out of the way. P-values. You can think of that like probability values. Essentially, a p-value measures the likelihood or the probability that you would get a test statistic as rare or as extreme as what you did. So of what you came up with. So a p-value is measuring the probability that the test statistic would be that extreme or more extreme, meaning farther away from the mean. So that's going to be a p-value. It's a measure of how extreme or how rare is it. Now, when we deal with p-values, we're going to compare p-values to our significance level. But first, let's look at these p-values and how we find them. Okay, if we have a left-tailed test, then what we're going to do is we are going to use our test statistic to find the area to the left, and that's going to come straight from our table. So we're going to use the z-score or the t-score. We'll use the z-score and look it up in the table and find the area, and the p-value will be equal to the area from the table. So we'll be able to read it directly from the table if it's a left-tailed test, because the table gives us the area to the left. If we have a right-tailed test, then we will find the z-score and look the area up in the table, but the p-value will be equal to 1 minus the area from the table. Because if it's right-tailed, we want the area to the right of that z-score, and the table gives us the area to the left. And if it's two-tailed, then the p-value is equal to 2 times the area in the tail. And I say area in the tail because if we're two-tailed, then that z-score that it gives us could be on the left-hand side of our distribution or on the right-hand side of our distribution. So we're looking for the area in the tail, so in the extremes. So if it's positive, if the z-score is positive, then we would be looking for the area to the right. If it's negative, we'll be looking for the area to the left. So basically, look at it as the area in the tail is always going to be less than 0.5. Think about a standard animal. Think of a cat. And don't go for one of the ones with really fluffy tails that looks like it's bigger than the rest of it. But if you think of a cat, or you think of most animals, their tail is small in comparison to their body. And so when we're talking about the area in the tail, we're talking about a small portion of the whole distribution, not a large portion. So the area in the tail is always going to be less than half, which means when you double the area in the tail, because you have a two-tailed test and you're finding a p-value, that will always give you a p-value that's less than 1. Okay, so that's going to give us our p-value. Well, why do we have these p-values? Because the p-value is going to allow us to do the test. And what I mean by that is once we have a p-value, if that p-value, let me just switch colors, if that p-value is less than or equal to alpha, our significance level, we're going to reject the null hypothesis. So which is basically saying if that z-score causes so the area in the tail is smaller than the significance level, which is what we're considering to be a rare event, then we're going to reject the null hypothesis because it's basically saying that it would be very unlikely that if the claim were true, or if the null hypothesis is true, that we would get a z-score that extreme. And if the p-value is greater than alpha, then we know we don't accept the null hypothesis. We don't do that. We fail to reject the null hypothesis. Remember back to that it's always easier to reject some general statement than to prove a general statement true? Well, that's what we're looking at here. We can say it's rare enough that we can reject the null hypothesis. But we can't say that it's likely enough that we can accept it. We either reject a null hypothesis or we fail to reject the null hypothesis. Now, if you don't tell my wife, I'll tell you a secret, that whenever my wife and I have a disagreement about something, either I can prove she's wrong or I can't prove she's wrong, but I never admit she's right. Right? Either I reject the null hypothesis, I reject what she's saying, and I can prove it, or I am unable to reject what she's saying, but I don't accept what she's saying. It's just a matter of I can prove it or I can't. I can prove it wrong or I can't prove it wrong, but it's never right. Now, don't tell her about that. It's not true. Sometimes I accept what she says as being right. Okay? I'm not that bad of a husband. But we get into this thing where we have to either reject a null hypothesis or we fail to reject a null hypothesis. We never accept a null hypothesis. And we're going to use this to come up with our method of making final statements about claims. In fact, we're going to go right to that right now. Because remember, we've got two things that can happen. Our claim can either be the null hypothesis or the alternative hypothesis, right? Depending on whether it includes equality. And we can either end up rejecting the null hypothesis or failing to reject the null hypothesis. And those things combining allow us to make a statement about the claim. So let's put a little table together here and get what our final statement would be as we go through this. So remember, possibilities are we reject the null hypothesis or we fail to reject the null hypothesis. Either the claim is the null hypothesis or the claim is the alternative hypothesis. So these are the four pieces we're going to put together. This kind of looks like a contingency table, doesn't it? And actually, I'm going to do a slight modification here. I'm going to put these in red so it shows up nice and clearly. Null hypothesis, alternative hypothesis. And I'm doing this because I want you to be able to see what part of these final statements come from which part of this. If we reject a null hypothesis, that means we were able to reject it. Remember, either I can prove she's wrong or I'm unable to prove her wrong, but I never accept that she's right. So if I can reject the null hypothesis, that means there is sufficient evidence. There is sufficient evidence. In fact, it goes all the way across. There is sufficient evidence. If we're able to reject the null hypothesis, there is sufficient evidence. There is enough evidence. If we fail to reject the null hypothesis, remember that just means that I wasn't able to prove it. There was not enough evidence, so there is not sufficient evidence. There is not sufficient evidence. Okay, so if we reject the null hypothesis, there is sufficient evidence. If we fail to reject the null hypothesis, there is not sufficient evidence. That's what comes from whether we reject or fail to reject the null hypothesis. The other part of this is, what was the claim? If the claim was the null hypothesis, and we rejected the null hypothesis, didn't we just reject the claim? If the claim was the null hypothesis and we rejected the null hypothesis, we just rejected the claim. If the claim was the null hypothesis and we failed to reject the null hypothesis, we didn't have enough evidence to reject the claim, right? So if the claim is the null hypothesis, to reject the claim. To reject the claim. The claim was the null hypothesis, that adds to reject the claim. Claim was the null hypothesis, we reject the null hypothesis, there is sufficient evidence to reject the claim. The claim is the null hypothesis and we failed to reject the null hypothesis, there is not sufficient evidence to reject the claim. We failed to reject the null hypothesis, which was the claim. Now, if the claim is the alternative hypothesis, and we rejected the null hypothesis. Remember that the alternative hypothesis is the complement of the null hypothesis. So if the claim was the alternative hypothesis and we rejected the null hypothesis, we rejected everything but the claim. Therefore, there is sufficient evidence to support the claim. So that means we have enough evidence to support the claim. If the claim was the alternative hypothesis and we failed to reject the null hypothesis, so we weren't able to reject everything else, then there's not sufficient evidence to support the claim. So if the claim is the null hypothesis, that adds to reject the claim. To reject the claim. If the claim was the alternative hypothesis, that adds to support the claim. To support the claim. And we can pull this out of every hypothesis test that we do. We'll get to the point where we'll look at a such and such significance level. So we'll always state our significance level. Just like with confidence intervals, we always stated a 95% confidence interval for such and such, a 98% confidence interval. Where here we say at a significance level, and I will point out that significance levels are kind of the complement of confidence levels. So if you had a 90% confidence level, 0.90, the associated significance level would be the other 0.10, the other 10%. So significance levels tend to be 0.10, 0.05, 0.02, 0.01. Right? So those are our significance levels. So our final statements will always be, at a such and such significance level, there is or is not sufficient evidence to reject or to support the claim. And so we'll work our way through it. And we will, as we deal with large samples and small samples and population proportions, we will go through this over and over again. But that's an introduction to hypothesis testing.